This lesson is an introduction to the unit circle. So let me first explain why it's called the unit circle. A unit of length means 1. So we might be talking unit fractions have numerators of 1, like 1/5, 1/3. A unit of length in inches would be 1 inch. So when we talk about the unit circle, it means that we have a circle that has a radius of 1. So if we go 1 unit to the right, then we're going to land right here, and the coordinates of this point will be 1, 0. If we go 1 unit up from the origin, we're at 0, 1. We go 1 unit this way, we're at negative 1, 0. We go 1 unit down, we're at 0, negative 1. Now, if we look at that in terms of angles opening, if we start here with both rays pointing in this direction, we're at 0 degrees. If I open my angle so that I've got one ray pointing here still as my base and the other ray pointing up, then I have a 90-degree angle. If I keep opening my angle, now I've got a 180-degree angle. Keep opening my angle even more, I've got a 270-degree angle. And then all the way around is 360 degrees, and I'm back where I started. You can also see that I can name locations by the quadrants. We have quadrant 1, that's between 0 and 90 degrees. Quadrant 2 is between 90 and 180 degrees. Quadrant 3 is between 180 and 270, and quadrant 4 is between 270 and 360. So we're going to start by taking a closer look at quadrant 1. So I've broken quadrant 1 up into several special angles. So here's my 0 degrees. Again, here's 90. But I've broken this quadrant up into a 30-degree angle, and then a 45-degree angle, and then a 60-degree angle. Now, we can do that in every quadrant. So if you notice, from the 0, I go 30 degrees. Another 15 will get me to 45. Another 15 will get me to 60. And then another 30 will get me to 90. So it's 30 degrees, then 15 and 15, and then another 30 degrees. Those are the angles that I'm looking at. And I can go all the way around the circle in this same pattern. I go 30 degrees, and then from there I go another 15 to get to 45, another 15 to get to 60, and then another 30 to get to 90. And then I keep going. Add 30, add 15, add 15, add 30. Add 30, add 15, add 15, add 30. Add 30, add 15, add 15, add 30, and I'm back at 360 degrees. You can also look at it as from 0, I add 30, and then go back to 0, add 45, go back to 0, add 60. So then from this angle, I'm going to add 30, and I would go back to this angle and add 45, and go back to this angle and add 60. So you could look at it that way as well, and that will be following this 30-degree, 45-degree, 60-degree pattern. Now you might be wondering, why are we looking at these angle measures in particular? And it's actually going to go back to something that you learned in geometry when you learned about special right triangles. But before we get to that, I just want to give you an idea of where we're going, why we're looking at those specific angles. There's another way that you can measure angles of rotation around the circle besides degrees. And the other way that you can measure it is something called radians. So radians are a measure of angle, just like a degree is a measure of an angle, but it's a different measure, sort of like I can measure length in inches, or I can measure length in feet or in miles. Well, I can measure angles in degrees, or I can measure angles in radians. And you know it's in radians because it'll have a pi in it. The way that we convert from degrees to radians is by multiplying by pi over 180. So let's try that with a few angles. Let's try 30 degrees. If I want to convert 30 degrees to radians, I have to do 30 times pi over 180. Now, in order to multiply a whole number and a fraction, I'm going to make them both fractions. And then I can do a little bit of canceling here. So for my answer, I'll get pi over 6. So 30 degrees is the same thing as pi over 6. All right, let's try another one. Let's try 45 degrees. So 45 degrees is going to be 45 times pi over 180, right? And again, I'm going to make that 45 a fraction, and I can do some canceling. And I get pi over 4. So 45 degrees is pi over 4 in radians. All right, let's look at 60 degrees. 60 degrees, I'm going to have to do 60, and I'll just write it over 1. You know why I'm doing that. Times pi over 180. I can cancel, and I get pi over 3. So 60 degrees is pi over 3. And let's just do one more. So we've got that whole first quadrant done. 90 degrees, I'm going to do 90 times pi over 180, do some canceling, and I get pi over 2. So 90 degrees is pi over 2. So you can keep going around the circle and fill in all of the angle measures in the same way, in radians. So once you do that, it looks like this. So we can see here are the ones that we converted already, right? Those are the 4 that we did. And we can keep going. We can multiply 120 by pi over 180, multiply 135 by pi over 180. And we can keep going all the way around. Notice that 180 degrees is pi. Keep going, multiplying each degree measure by pi over 180. And then when we get back to 360, that's 2 pi. So all the way around the circle is 2 pi. That's important to remember because the angles that you're going to need to remember the most are the multiples of 90. So this one, this one, this one, and this one. So remember that if this is 0 and all the way around is 2 pi, well then it would make sense that halfway around would just be 1 pi, and half of that would be pi over 2. All right. So now let's look at why it is that we're looking at these specific angles. Remember I told you that the reason we're looking at the 30 degree and the 45 degree and the 60 degree has to go back, or has to actually, comes from, something that you learned in geometry. And in geometry, you learned about 2 types of special right triangles. One was an isosceles right triangle, which is shown here on the left. It's a 45, 45, 90. And the other one is a 30, 60, 90. So we're going to start with the 45, 45, 90. And what you learned when you investigated these triangles was that there was a pattern that you could use so that you didn't have to do Pythagorean theorem every time. It was kind of like a shortcut if you needed to find a leg or the hypotenuse. Whatever the measure of the leg was, to get the hypotenuse, you would just multiply that leg by root 2. So for example, if you were given that the leg is 3, then this leg is also 3, and this leg would be 3 root 2. Right? Hopefully that rings some bells and you remember learning about that a little bit in geometry. If not, then all you need to know is that the pattern is whatever the leg measure is, you just multiply that by square root of 2, and it'll give you the hypotenuse. Now, if you don't want to memorize that, you can use Pythagorean theorem, but you're always going to get this same result. So this is sort of just like a shortcut so that you don't have to do the Pythagorean theorem. All right, in a 30, 60, 90 triangle, we have one leg that's longer than the other. So the pattern that we see in a 30, 60, 90 is that you take the measure of the short leg, and that measure is what's going to determine these other two sides of the triangle. So you take the short leg and double it to get the hypotenuse. You take the short leg and multiply it by square root of 3 to get the longer leg. Okay, that's the pattern. Now the reason why, because just like we said over here, you can do Pythagorean theorem and you can find it, but this is just kind of like a shortcut through the calculation, so you don't have to do the calculation every time. We're using patterns to help us. So over here, this triangle, a 30, 60, 90, and I don't have enough room to draw it in here, but if I could, I would draw a triangle that goes all the way down here. It's actually half of an equilateral triangle, right? And this angle down here would be 60 degrees. So because it's half of an equilateral triangle, that's why this whole side would be 2x, half of it would just be x, and this side would be 2x. Okay, so that's why we have the doubling thing. So you take the short leg, double it to get the hypotenuse, and take that short leg again, multiply by root 3 to get the long leg. All right, now let's look at each one of these and how it applies to the unit circle. So here's our pattern, right? The leg is x, the other leg is x. We're going to look at the 45, 45, 90 triangle first. And then I take my leg measure and I multiply by root 2. But I have a question for you. What if? So I'm going to draw my triangle in right here. And I know that since this is the unit circle, that means that my radius is 1. So that means that this hypotenuse has a measure of 1. So the question is, I know that if I have the leg, I have to multiply by root 2, right, to get the hypotenuse. But what if I'm given this length? What do I do to this to get backwards, to get back to what this length is? Think about it. If I know that this measure is 1, what do I have to do to that to get back to what the length of the leg is? Well, you can see that I have to get rid of this part, right? And since my x is being multiplied by root 2, the only way I can get rid of that root 2 is to divide by root 2. So in order to go from the leg to the hypotenuse, I have to multiply by root 2. In order to get back from the hypotenuse back to what the measure of the leg is, I have to divide by root 2. So in my triangle down here, my hypotenuse is 1. I'm going to have to divide that by root 2 to figure out the length of the leg. So let's do that. I'm going to have 1 divided by root 2. Now, it might look fine to leave it like that. But remember, when we were working with radicals not so long ago, that it's not simplified if we have a radical in the bottom. So the way to rationalize this is to multiply by that radical on top and bottom, and I get this. I get root 2 over 2. So that is the length of the legs of my triangle. So this leg is root 2 over 2, and this leg is root 2 over 2. So now I can come over to this diagram on the right and I can label it. This is root 2 over 2. This is root 2 over 2. This is root 2. Every time I see a leg, I know that it's root 2 over 2. Right? And all my radii are 1. So why am I doing this? Well, the reason I'm doing this is so that I can write a coordinate for this point. I know that this point is 1, 0. I know that this point is 0, 1. But in order to get to this point and write the coordinates, I need to know how many over and how many up I need to travel to get to this point, right? So now I found those distances. I have to go root 2 over 2 to the right, and then root 2 over 2 up. So the coordinates of that point would be root 2 over 2, root 2 over 2. What about the coordinates of this point? Well, for this one, to get to this point, start from the origin, I have to go negative root 2 over 2. So I go root 2 over 2 to the left, and then I go up root 2 over 2. So the coordinates for that point would be negative root 2 over 2, and then up 2 over 2. What about this point? Well, to get to this point, I have to go left root 2 over 2, and then down root 2 over 2. So the coordinates for this point and then lastly, the last point that I have here to label, I would have to go right root 2 over 2 and then down root 2 over 2. So my coordinates would be and now I filled in the coordinates for those 4 points using what I know about special right triangles. Now let's look at the other type of special right triangles and how it's going to help us with the unit circle. So the other type of special right triangle is the 30, 60, 90 right triangle. And again, the pattern is whatever the short leg is, we double it to get the hypotenuse, and then we multiply by root 3 to get the long leg. So let's look at the 30, 60, 90 triangle, and we'll start with this point right here at 30 degrees. So this is our angle, and the symbol that you're going to see to represent the angle is called theta. It looks like this. So that's the angle that we're looking at, and this is a right triangle. So this is our short leg, right? So whatever the short leg is, we double it to get the hypotenuse, and whatever that short leg is, we multiply by root 3 to get the long leg. But remember, this is a unit circle. So in the unit circle, that means that the radius is 1. So that means that this value is 1. If the hypotenuse is 1, what should the short leg be? Well, look at your pattern. We know that whatever the short leg is, we have to double it to get the hypotenuse. So if the hypotenuse we know is 1, then what number doubled would give us 1? Right, 1/2, right? Because if I double 1/2, I get 1. And then to go from the short leg to the long leg, I have to multiply by root 3. Well, 1/2 times root 3, you can write it like that, is root 3 over 2. So that's what this one's going to be, root 3 over 2. So now let's fill that in over here. So that means that if I fill this triangle in, that in order to, I know that my long leg here is root 3 over 2, and my short leg is 1/2. So in order to plot this point right here, I would have to go over root 3 over 2 and up a half. So that would be over root 3 over 2 and up a half, right? So now let's look at the other. Let's look at the 60-degree angle. So now I'm looking at this triangle. Sorry, that's supposed to be a box. And again, my radius is 1. And if my radius is 1, the hypotenuse is 1, that means that this short leg down here is a half. And that my long leg here is going to be root 3 times that. Right? So now I can fill in this triangle. I know that this part is a half. The short leg is a half, right, because this is 1. And my long leg is root 3 over 2. Because I'm just orienting the triangle a different way, right? So in order to plot this point, I would have to go 1/2 to the right and root 3 over 2 up. So my coordinates here would be 1/2 root 3 over 2. Okay, so now let's look at 120 degrees. So here's what my triangle would look like. Right, so I would have to go, to get to this point, I would have to go the short leg, which is a half, right? 1/2 to the left, and then root 3 over 2 up. So 1/2 to the left, root 3 over 2 up. All right, now let's look at 150 degrees. So for this one, to plot this point, I would have to go the long leg to the left, which is root 3 over 2, and then 1/2 up. So that would be negative root 3 over 2, and then a half up. Because remember, the long leg is root 3 over 2, the short leg is a half. All right, we're going to keep going. Let's go down to this one. To get to this point, 7 pi over 6, or 210 degrees, I would have to go the long leg to the left, and then the short leg down. So that would be the long leg to the left would be negative root 3 over 2, and then the short leg down would be negative a half. All right, let's go to the next one, 240. So this triangle, to get to this point right here, I would have to go the short leg to the left, and then the long leg down. So that's going to be the short leg to the left, and then the long leg down. And let's keep going. We've got 2 more to do. We're going to look at this point next. So to get to that point, 300 degrees, I would have to go short leg to the right, long leg down, which is going to be short leg to the right would be a half, long leg down would be root 3 over 2. And one more. To get to 330 degrees, I would have to go long leg to the right, short leg down. So that's going to be root 3 over 2. And then, oh, I forgot to make this one negative down here because I went down. And then negative a half. All right. So that's how we would fill in all of the rest of the coordinates. So with everything filled in, this is what we get. And now you know where all of these values come from. So something to keep an eye on is where things are positive and where things are negative. So in the first quadrant, everything's positive. In the second quadrant, our x value is negative and our y value is positive. In our third quadrant, they're both negative. And in the fourth quadrant, we've got a positive x and a negative y. So that's going to come in, that's going to become very useful. And then I've got a blank unit circle for you to practice filling in the values, because it is going to become very important for you to be able to fill in the values and know where everything goes. The more familiar you are with this unit circle, the easier the problems in this section will be, and the easier time you'll have doing these different trig graphs and trig functions.